Alright guys, here's your notes packet for section 5.5. Hopefully you've watched 3 short videos that I assigned to you on Edpuzzle before this. It'll really help just with the conceptual understanding of some of the topics we go over here. So the first thing we want to do is talk about the most stable shape. And the most stable shape, as you should have learned in that one video, is the triangle. That's why when you go and look at the construction of new houses and things, you see almost everything's constructed of triangles. So if we look at these 2 benches that these football players are sitting on, we see that this one here, right here, is basically constructed of 2 triangles, okay? So it's like a rectangle, but then there's a diagonal that makes 2 triangles. And then the other one over here doesn't have that diagonal piece, it's just a straight up rectangle. So because this is composed solely of triangles, this is stable. Because this is not composed solely of triangles, this is not stable. And in other words, these players run the risk of this bench collapsing on them when they set on it. Alright, so if we look at a few examples here, we want to decide if these are stable or if they are not stable. Now this one is not stable. And the reason is because it looks like a square. Now to make it stable, we could either draw this diagonal here, or we can draw this diagonal here. Now we don't have to draw both, just one will do. That would make it stable, but as it is not stable. This one, notice, is composed solely of triangles, so this is stable. Okay, if we look over here, this part is stable, but this part down here is not stable, meaning that the whole structure is not stable. Now if we wanted to make this stable, we could put a diagonal either here or a diagonal here. We don't have to have both, and that would make it stable, but as it is not stable. Alright, let's turn our attention now to the side-side-side congruence theorem, or a lot of people just call it SSS. If you see SSS, just know that it stands for side-side-side. Now this theorem tells us, as you should have learned in that short video, if all 3 sides of 2 triangles are congruent to the other 3 sides of the other triangle, then these triangles have to be congruent triangles. So because the 3 sides of the right are congruent to the 3 sides of the left, that ensures that each of the angles over here are also congruent, which means the whole entire triangle are congruent, okay? So all we need to know are the 3 sides, and that's a shortcut to say the triangles are overall congruent. Alright, so let's look at an example here. Okay, well, by the tip marks, we know that this side and this side are congruent. We know that this side and this side are congruent. And then we know this side up and down, sorry guys, and this side up and down are congruent. So we could say, yes, these triangles are congruent by the side-side-side congruence theorem. Alright, this side, we have 7 and 7, so that's a good start. They share this side 9, so 9 and 9, but notice we have 3 and 4, okay? So these would not be congruent, okay? We don't have a side-side theorem, we have a side-side-side theorem. So just because 2 of these sides are congruent, the third isn't, they are not congruent triangles. Alright, let's look at 3 over here. We know that this and this are congruent, this and this are congruent, and 1, 2, 3, and 1, 2, 3 are congruent. So side-side-side congruent theorem, we could say yes, these 2 are congruent. Alright guys, we're going to get back into proofs pretty heavily in the last few sections here, but these proofs will make more sense than the proofs that we did in chapter 2, so that'll be good. Most of them you guys will think are a lot easier. Alright, so we want to prove that these 2 triangles are congruent. Okay, so let's start. So we are given that KL is congruent to NL, and we are given that KM is congruent to NM. those two are given. All right, well, if I look up here, KL and LN, and then I have KM and NM. Okay, well, notice the only side that I'm missing is this middle one right here, and they share this side. Okay, so that's where the reflexive property comes in. So I can say that LN is congruent to LM by the reflexive property. Now notice I've shown one set of sides is congruent, another set of sides. All three sides are congruent. So I can say that triangle KLM is congruent to triangle NLM by the side-side-side congruence theorem. All right, we're going to talk about another theorem. It's the hypotenuse leg theorem. But before we do that, we need to define what a hypotenuse is. Okay, so the hypotenuse is the side of a right triangle that is opposite of the right angle and it will always be the longest of the three sides. Okay, so if I have a triangle here, and if I know this is my right angle, the side opposite of this angle would be my hypotenuse. Okay, so it's always opposite of a right triangle. So I'm going to write something in big red here. So the only time you have a hypotenuse is when you have a right triangle. Okay, you can't have a hypotenuse if you don't have a right triangle. Okay, so the hypotenuse leg theorem tells us if you know that the two hypotenuse are congruent to each other, remember, and the hypotenuse is opposite of the right angle, and one of the two legs, that's enough to determine that these two triangles are congruent. There was also a very short video on the hypotenuse leg theorem as well. All right, let's do an example using the hypotenuse leg theorem. All right, so before I do this, I want to go ahead and separate these triangles. So notice I'm trying to prove that triangle WYZ is concurrent to XZY. Okay, so these triangles overlap. So some of you, that'll make it very confusing. So I'm just going to draw it separately. Okay, I'm going to pull them apart and draw them separately. All right, so the first thing I know is WY is congruent to XZ. That's given. So I'm going to go ahead and draw it. WY is congruent to XZ. Okay, then I know that WZ is perpendicular, remember that upside down T is perpendicular, to ZY. That's given. And XY is perpendicular to ZY. That's also given. All right, so then you need to ask yourself, what does it mean for two segments to be perpendicular? If two segments are perpendicular, that means they intersect at a right angle. So that means that WZ and ZY, that means angle WZY is a right angle. And it also means that XY is perpendicular to ZY, so XY here is perpendicular to ZY here, so that means that angle XYZ is a right angle as well, and both of these are just by definition of perpendicular. All right, now if I look at this, when they're separate, I don't see anything else. I just know that we have a right angle and a hypotenuse that are congruent. Now notice, this is a hypotenuse, right? Because it's opposite of a right angle. Okay, but if I look back at the figure here, where they're joined, don't they share this side? Isn't that ZY and YZ here? So I could say YZ is congruent to YZ. That's by the reflexive property. Okay, well now I have a right angle, I have the hypotenuse, and I have one of the two legs, so I can say that triangle WYZ is congruent to triangle XZY by the hypotenuse leg theorem. Alright, I want you to go ahead and try to do this one on your own, and then we will go over it. Alright, so let's go over this. So we're given that AE is perpendicular to all these different lines. Okay, so that's just given. So AE, the center, is perpendicular to all these lines that go out, which means that each of those angles formed are right angles. That's just the definition of perpendicular. Anytime two lines are perpendicular, that means they form a right angle. Okay, and then we're also given AB is congruent to AC, which is congruent to AD. So that's given. Now notice, with those the right angle, these sides are the hypotenuse of each of these right triangles. Okay, they're opposite of the right angle, opposite of the right angle, and opposite of the right angle. Okay. And then, so I have a hypotenuse, I need another leg, so I need one of the other two sides. Notice, guys, they all share AE. Okay. This is a side of each of those three triangles, so I can just say, since there's three triangles, I put AE is congruent to AE is congruent to AE. Usually when there's two, it's just AE is congruent to AE, but that's the reflexive property. Now, by the hypotenuse leg theorem, we can say that each of these three triangles are congruent. Alright, let's look at this final example. It first wants us to redraw triangle ABC and triangle DCB so that their corresponding parts are in the same position. So I'm just going to redraw triangle ABC on the left to look like BCD on the right. Okay, so think of it like a rotation of 180 degrees. So C, B, A. Okay, and I know AC has one hash mark, and I know angle B is a right angle. Okay, so now I can just disregard this. All right, now I want you to try to write this proof on your own, and then we'll go over it. All right, so hopefully you were able to get this by yourself, but we're given that AC is congruent to BD. That's given from the diagram. See, guys, they have tick marks on both. Okay, we're also given that angle BCD and angle CBA are right angles. That's also given. Okay, now if we look back to this original picture, this here, BC, so here's BC, they share this. So I can say BC is congruent to BC. That's the reflexive property. Okay, and now, because I have a right angle, this is my hypotenuse. So here's my hypotenuse. Here is a leg. I can say that triangle ABC is congruent to triangle DCB by the hypotenuse leg congruence theorem.